This is lecture 1F, and we're going to talk about ionization of acids. According to Bronsted-Lowry, an acid is a substance that releases a hydrogen ion to something else, donates a hydrogen ion. When acid molecules are placed in water, it's water that the acid molecules donate their hydrogen ion to. If we take hydrogen fluoride as an example, when hydrogen fluoride is dissolved in water, the hydrogen fluoride molecule will donate its hydrogen ion to the water, creating a hydronium ion and a fluoride ion. This is the reason that HF is an acidic material, because it creates hydronium ions in solution. And that's why when it's dissolved in water, we don't name it hydrogen fluoride, we name it hydrofluoric acid. Let's see if we can write the equilibrium constant expression for this reaction, because when acids react with bases, in this case water's acting as a base, it produces the products, in this case hydroniums and fluorides, and the reverse reaction occurs as well, and eventually you reach an equilibrium. So the equilibrium constant expression for the reaction of an acid ionizing in water would be products over reactants. It would be the molarity of the hydronium ions multiplied by the molarity of the fluoride ions, divided by the molarity of hydrofluoric acid, and then that would be it, because water's a liquid, and liquids don't appear in equilibrium constant expressions. Anytime you have an acid ionizing in water and this system reaches equilibrium, the equilibrium constant for that reaction is given a more specific name than just the KEQ or the KC. It's called the acid ionization constant, and it's abbreviated K sub A. It's the equilibrium constant for the reaction of an acid donating a hydrogen ion to water. So if we want to be more specific, we can erase the KEQ and replace it with a Ka. So any acid, when it reacts with water, will produce hydronium ions and then an anion, and we can write an equilibrium constant expression for that, and the ratio of the product molarities to the reactant molarities will equal an equilibrium constant that we will call the acid ionization constant. Now, we've already discussed acids can be strong or weak. An acid is strong if every single acid molecule gives up a hydrogen ion to a water molecule. If we think about the equilibrium constant expression we just wrote for HF, if that were a strong acid, then we would produce lots and lots of hydronium ions and fluoride ions, which go in the numerator, and we wouldn't have any HFs, which go in the denominator. That means your equilibrium constant, your Ka value, is going to be a large number. If you have a weak acid, then less than every acid molecule gives up a hydrogen ion. So that means you actually won't have very many hydroniums and fluorides. The numerator will be small, and the number of HF or acid molecules that stay associated together will be in the denominator, and that'll be a big number, and so your Ka value will be small. We have on our class website a handout 3 that lists lots of acid ionization constants. Here's a sample of that. Here's 4 different acids: hydrochloric acid, hydrofluoric acid, which we just saw, acetic acid, and hydrocyanic acid. Their Ka values are given. So these are the equilibrium constants for the reaction of the acid molecule reacting with water to form a hydronium ion and an anion. In a generic form, whatever the acid is, HX, reacting with water, it donates its hydrogen ion to the water becomes a hydronium, and then the acid, the HX, just becomes X minus, which is its conjugate base. The equilibrium constant expression for all of these acid ionization reactions are almost always identical. They're the hydronium ion concentration multiplied by the conjugate base's concentration divided by the original acid's concentration. Water's left out because it's a liquid. Now, if you look at the Ka values, they give you some information about the strength of the acid. Based upon these Ka values, which would be the strongest acid, it would have to be the one with the biggest Ka value. We've talked about before how hydrochloric acid is a strong acid. That means 100% of the HCl molecules actually react with water to form hydroniums and chlorides. If it really was 100%, that means the products, or the numerator in the Ka expression, would be some big number. And then the molarity of the HCl's in the denominator of the Ka expression would actually be 0. The actual Ka value would be infinity. So it really isn't exactly 100%, it might be 99.999% of them that actually ionize. But just by looking at the Ka values, if you see one with a really big positive exponent, like 10 to the 6th, that's a strong acid. And out of these 4 acids here, HCl is definitely the strongest. This is the one that most readily releases hydrogen ions, and thus the numerator of the Ka expression would be really, really big, and the denominator would be really small. The weakest acid here would have to be the opposite, the one with the smallest Ka value. That would be hydrocyanic acid. What this means is the HCN molecules stay bonded together. Not very many of them break apart into hydronium ions and cyanide ions. So they are least readily releasing hydrogen ions. So therefore, the numerator in the Ka expression is really small and the denominator is really big. What would be the Ka value for water? You take our little equation we have at the top right end of the slide here and imagine HX is water. What would that reaction be if water were the acid? Then the reaction would be water plus water yields hydronium ion plus, and then what would you have if a hydrogen was removed? Hydroxide ion. We've seen that reaction before. That's the ionization of water itself. The equilibrium constant expression for that is the concentration of hydroniums multiplied by the concentration of hydroxides. And then we wouldn't divide it by anything because in this case, the acid would be H2O liquid, so there'd only be liquids on the reactant side. We know what the equilibrium constant is for that reaction, and that's called the Kw. It's the ionization constant for water. Well, if water's an acid, it's also water's Ka. It's 1.0 times 10 to the minus 14th. So what does that tell you about the acidity of water compared to hydrochloric, hydrofluoric, acetic, or hydrocyanic acid? Well, water is less acidic than those because it has a smaller Ka value. So with water on this list, water would be the material that would be the least acidic. Methane is a compound that contains hydrogens in its formula. It's CH4. Is methane considered an acidic material? Usually acidic materials rewrite hydrogens in the front of their formula. Methane has its hydrogens at the back. What does that tell you? That tells you it's probably not an acidic material. And if we look at its Ka value, you can see its numerical value is 1 times 10 to the minus 5th, which means almost no methane molecules would release a hydrogen ion to water in a solution. So methane in this list would be the weakest acid of all. Now, if we want to calculate the pH of an acidic solution, it's going to be a different calculation depending upon whether the acid is a strong acid or a weak acid. So let's talk about strong acids first. When you have a strong acid, we assume they 100% ionize in water. So we'll assume complete ionization or dissociation. So let's take an example of a strong acid. Let's calculate the pH of 0.010 molar nitric acid. Nitric acid has 2 more O's and H's in its formula. That's why it's a strong acid. So if you want to predict what its pH is going to be, if you imagine what the nitric acid molecule would do if it dissolves in water, it would be the same reaction we just talked about. It would bump into a water molecule, donate its hydrogen ion, and create a hydronium ion and a nitrate ion. So to predict what's going to happen here, if we write an initial molarity, change in molarity, final molarity table, we're making a solution 0.010 molar in nitric acid, and we're assuming there's nothing else present in there initially. And so if some amount of that nitric acid reacts, we would put minus X under the nitric acid, plus X under the hydronium, and plus X under the nitrate ion. This is what we would do if we don't know how much of the nitric acid will react. But if it's a strong acid, we actually do. It's not an unknown amount. All of it reacts. So I'm not going to put X's here. If I know all the nitric acid reacts away because it's a strong acid, every single one donates a hydrogen to water, all 0.010 molar will react, and you will form 0.010 molar of hydroniums and 0.010 molar of nitrates. Adding up the columns then, there'll be no nitric acid molecules in the container, but there will be 0.010 molar of hydronium ions and 0.010 molar of nitrate ions. So if we know that this solution will be 0.010 molar in hydronium ions, pH is defined as the negative log of the hydronium concentration. So we're going to take the negative log of 0.010 molar. That concentration is a 2 significant figure number, so the pH is going to have to be given to 2 significant figures. And if you remember logarithmic numbers, the significant figures only appear past the decimal point. So we have to write the pH with 2 places past the decimal point. So the pH of this solution would be 2.00. When you're dealing with strong acids, you can actually predict the hydronium concentration much more quickly than writing out an initial change in final table. If you know the HNO3 is going to completely ionize in water and donate its hydrogens, then really all we have to do is take the molarity of the HNO3 and multiply by how many hydrogens are in the formula, which is 1. So 0.010 multiplied by 1 gives me the same answer I have in my final molarity line under the H3O plus of 0.010. So it can actually be done in a shorter way in that sense. Now, what if we have a weak acid? If you want to calculate the pH of a weak acid, the difference is it does not ionize completely. We assume incomplete ionization or dissociation, therefore reaching a state of equilibrium. So if we take an example of a weak acid, nitrous acid, we're going to see if we can calculate the pH of a 0.010 molar nitrous acid solution. So same molarity as the problem before, but now it's a weak acid. So what produces the hydronium ions? It's the reaction of the acid molecule with water. So you have to write nitrous acid, HNO2, plus water, transfer the hydrogen to make a hydronium ion, and then you have a nitrite ion remaining. We want to write an initial change and now equilibrium table for this because this reaction is going to reach equilibrium because it's a weak acid. So if we're starting with 0.010 molar of nitrous acid, there's nothing else in the container at first, then some unknown amount of the weak acid will react because it doesn't go to completion. We don't know what it is. Now we actually will call it X. You'll form X amount of hydroniums and X amount of nitrites. Add up the columns, it'll be 0.010 minus X for the molarity of the nitrous acid molecules. Here's the one that produces the acidity of the solution, and thus the pH, the hydronium concentration will be X, and the nitrite concentration will be X as well. So these equilibrium molarities are related to the equilibrium constant for nitrous acid ionizing in water, and that's called a Ka. So the Ka is going to equal the product of the molarities of hydronium and nitrite divided by the molarity of the nitrous acid molecules. I know my equilibrium values from my ice table. They're X and X on the top and 0.010 minus X on the bottom. We need to know the value of Ka. And this is why our class website has handout 3 in it. You can actually look up the Ka for many acids that are weak acids on that handout. So if we go to handout 3 and we look up the Ka for HNO2, it'll tell us its numerical value is 4.0 times 10 to the minus 4th. So now I can actually work on solving this problem by using that value as the Ka. So 4.0 times 10 to the minus 4th must equal X squared over 0.010 minus X. Now, to solve this, this is a quadratic. You can do it with the quadratic equation, and if you're the master of your calculator and like doing that, you're going to get the exact answer, and that's perfect. But if you don't want to have to solve the quadratic equation, we can do this by making an assumption. It actually introduces a little bit of error, but it makes the mathematics much more simple. And here's the concept. The equilibrium constant is really small. That means you don't have very many products at equilibrium. So the value of X is going to be a small number. That X squared at the top, those two X's are small numbers. That X at the bottom, 0.010 minus X, that X is a small number as well. Now, if that X in the denominator is a really small number then 0.010 minus a really small number really doesn't change the denominator much. It stays pretty close to 0.010. So we're going to make an assumption that X is so small that when it is subtracted from or even added to another number, it's going to be insignificant. We kind of assume it's 0. So you can do this for a weak acid if the Ka is less than 10 to the minus 2nd. If it's a small Ka, that means the acid does not ionize very much. So you can assume that the X is going to be very small, and then you can ignore it when it is subtracted from the initial molarity, and we can solve this problem instead. And this is way easier to solve. We just multiply by both sides by 0.010, and then take the square root, and you get a value for X. Now, when we set this up, I said by making this assumption, we're actually introducing an error. How much error are we really willing to accept? Well, generally, chemists are willing to accept 5% error. Now, how do we tell what the error is? we take what we got for x, 2.0 times 10 to the minus third, we divide it by the original amount of acid, it's what we subtracted the x from, 0.010, and multiply by 100. So we calculate how big x is relative to the initial molarity. If it's less than 5%, that's fine. We'll accept that small amount of error, and we'll assume this is our value for x, and x stood for the hydronium ion concentration. If x values are greater than 5% of the original acid molarity, then that means our assumption really isn't very good, and we've got to do something else. We're going to take our value for x, the 2.0 times 10 to the minus third, we're going to place it back in the place of x in the equation at the very top of the slide, and we're going to solve for x again. So in this case, let's see if we need to do that. I'm going to do a little test here. I'm going to take my x value, 2.0 times 10 to the minus third, divide it by what the original molarity was, what I'm subtracting the x away from, and multiply it by 100. Let's see what we get. If we get less than 5%, then we're fine. But in this case, we get 20%. So that means our assumption of x being so small that it's kind of like 0 in the denominator really wasn't a good assumption to make. So what we're going to do is we're going to make a better assumption than assuming that x in the denominator is 0. We're going to assume the x in the denominator is 2.0 times 10 to the minus third. And those are the directions in green here. It says if the x values are greater than 5% of the original acid molarity, which it is, it's 20%, the x value should be put back in place of x in the denominator of the Ka expression and solved again. So I mean to put 2.0 times 10 to the minus third in that position for x in the denominator instead of assuming it was 0. And we're going to solve this again. You do the subtraction, you multiply, and then you take the square root. So here I get x equal to 1.8 times 10 to the minus third, or 1.79 times 10 to the minus third with a guard digit. How do we know if this is a better answer or a worse answer? Well, what we're going to do is we're going to repeat by placing our x value into the denominator of the Ka expression until we get the same answer twice in a row. What happens is if you successively do this, then your values for x will get closer and closer to the right value that you would have gotten if you would have done the quadratic equation. So now I'm going to take my 1.79 times 10 to the minus third and put that in the denominator where I have the 2.00 times 10 to the minus third written. So you can see I'm just replacing it in one more time. This is called recycling. You subtract the denominator, multiply it over, take the square root, and now when I do it again, I get 1.8 times 10 to the minus third. The answer needs to be two significant figures because the constant was two significant figures and the molarity of the nitrous acid was two significant figures. So I've now got the same answer twice in a row. They're both 1.8 times 10 to the minus third. So when you get the same answer twice in a row, you're done. You've actually achieved the two significant figure answer you would have gotten if you would have done the quadratic equation. So once we have x, if you go back to the ICE table, what was the hydronium ion molarity at equilibrium? It was x. So we now have the hydronium ion concentration. If we want the pH, we take the negative log of that. And because the hydronium concentration is two significant figures, when we get our pH, which is a logarithmic number, it has to have two places past the decimal point to be a two significant figure number. And so this acid should have a pH of 2.74. So same concentration, two problems in a row for nitric acid and nitrous acid. The nitric acid, which is a strong acid, had a pH of 2.00. Nitrous acid, which is a weak acid, has a pH of 2.74. They're both below 7. They're both acidic solutions, but the nitric acid with the 2.00 pH was more acidic than the nitrous acid with the 2.74 pH. Now, before we try one more example of this, let me point out something that's sometimes a little bit confusing. We had to do the recycle because the value we got for x was 20% of the original molarity of the acid. When you recycle and you put the 2.00 times 10 to the minus third back in place of x in the denominator, and then you get the next answer and put 1.79 times 10 to the minus third in place of x in the denominator, we continue to do this till the x value is the same. We will never make the value for x less than 5% of the original 0.010 molar. This is just a problem where the percentage that x is of the original amount is just a high number. So actually our final answer of 1.8 times 10 to the minus third was 18% of the original value. So don't think that that percentage is going to go all the way down under 5 and that's when you're done. That'll never happen. What you're trying to do is just get the value for x to be the same twice in a row. If you want to try one of these on your own, let's see if we can calculate the pH of a 0.20 molar acetic acid solution if, from handout 3, its Ka is 1.8 times 10 to the minus fifth. And then I'll go ahead and do that. If you want to pause to see if you can first, that would be fine. So acetic acid is HC2H3O2. The way it produces hydronium ions is it bumps into a water molecule and it transfers its hydrogen ion to the water molecule, creating a hydronium ion, and then you get the conjugate base of acetic acid, which is the acetate ion. So this is the traditional reaction you're always going to have when you're dealing with an acid and you're trying to determine what its pH is, because this is how the hydronium ions are created. We write an ICE table for this. The acetic acid's initial molarity is 0.20. And before any of it ionizes, we wouldn't have any products from the acetic acid, so there would be none of these. Because it has a Ka value that doesn't equal 10 to the 6th or infinity, we know it's a weak acid, so therefore some unknown small amount of it will react away. It'll be 1x, and it'll form 1x of hydroniums and 1x of acetates. Adding the columns, we'll get 0.20 minus x molar for acetic acid, x molar for hydroniums, and x molar for acetate. These equilibrium molarities are related to the equilibrium constant for this reaction, which is the Ka of acetic acid. So the Ka of acetic acid will equal the hydronium ion molarity multiplied by the acetate ion molarity divided by the acetic acid molarity. And I know the Ka value, and I plug in all my equilibrium molarities to the right side of the Ka expression, and now I have an equation I can solve for x. You can do it by doing the quadratic formula, or because the Ka is less than 10 to the minus second, we can make an assumption. And we're going to assume that x is so small that the denominator is probably going to be really close to just 0.20. I'm just going to assume the x in the denominator is 0. I'm going to solve this instead. And when I solve this expression by multiplying both sides by 0.20 and taking the square root, I get 1.9 times 10 to the minus third. Now, was that a good assumption? We're going to have to do a test. So the way we test to see if it was a good assumption that the x in the denominator was so small we can ignore it is we're going to take our value for x, 1.9 times 10 to the minus third, and divide it by the molarity of the acid we subtracted it from, the 0.20. So that'll be 1.9 times 10 to the minus third divided by 0.20 multiplied by 100. If this comes out less than 5%, the assumption was good. We can use our value for x. We're done. If it comes out greater than 5%, then I have to do the recycle process. But this came out even less than 1%, only 0.95. So that means the x value can be assumed to be correct, and x stands for the hydronium ion molarity. So if you want to get the pH of the solution, you take the negative log of 1.9 times 10 to the minus third, which is a 2 significant figure number. So your pH will have 2 places past the decimal point. The acetic acid solution's pH should be 2.72. Now, something else you can calculate concerning weak acids is you can calculate the percent ionization. Very similar to how we did things like this in our equilibrium chapter. If you want the percent ionization of acetic acid, go to the ICE table where acetic acid is. Look how much changed. That's how much ionized. It says X there. How much did you start with? 0.20. So take your X value, which we know is 1.9 times 10 to the minus third, divide it by 0.20 and multiply it by 100. So the percent ionization is the amount dissociated, or the amount ionized in this case, divided by the original amount, multiplied by 100, and we have those numbers. This comes out 0.95%. You may notice the little test we do to see if the assumption of X being very small was good or not is the exact calculation you would do if you're trying to calculate the percent ionization. Now, let's see if we can go the other way around. Let's say we want to calculate the Ka of a weak acid. You can do this as long as you have one additional clue in the problem, and one of the potential clues you could have is the pH. This can be easily determined. You take a weak acid solution and you stick a pH probe in, and it tells you what the pH is. So if you can use a pH probe, you can actually calculate Kas of weak acids. So let's say we have a 0.500 molar solution of the weak acid HA, and it's found with a pH probe to have a pH of 2.010. Let's calculate its Ka. So to do this, we're going to need to know all the equilibrium molarities of the species present when HA dissolves in water. So we have to do an ice table because we're only given an initial molarity of HA. We need the equilibrium molarities. And the reaction you have to write for a Ka is the reaction of the acid with water. So it would be HA plus water yields, and then the HA donates its hydrogen ion to the water, producing a hydronium ion, and then you would get the conjugate base of HA, which would be the anion A-. If we write an ice table for this, they said initially in the solution, the molarity of the HA was 0.500, and before any of it ionizes, there wouldn't be any hydroniums and there wouldn't be any A- in there either. If it's a weak acid, we don't know how much ionizes, so we'll call that minus 1x. You'll form plus 1x of hydroniums and plus 1x of A-. The equilibrium molarities of all three will be 0.500 minus x, and x. And now that we know the equilibrium molarities algebraically, they're all related to the equilibrium constant for this reaction, which is HA's Ka value. So the Ka will be hydroniums multiplied by A- divided by HA molarities. So we don't know the Ka, but we do know the equilibrium values from our ice table. And here we have a situation that we've seen before. We've got two variables in the problem. We need to figure out x first before we can get Ka. So there's got to be something in the problem, a little clue that's going to allow us to calculate what x is, and that clue is the pH. The pH is the negative log of the hydronium ion concentration, which is x. So the pH is the negative log of x. If you want to solve for the hydronium ion concentration, we have to move the negative sign to the other side of that equality and take the antilog. So because x equals the hydronium concentration, and the hydronium concentration will be the antilog of the negative pH, if we take the antilog of negative 2.010, we'll know the hydronium concentration, and that's going to be the value for x. Now, our pH, 2.010, has 3 places past the decimal point. It's a 3 significant figure number. So now when I calculate the molarity of the hydronium ions, that's non-logarithmic number. So we just write 3 total digits altogether. So 0.00977, and then I have a guard digit there for 2. But this would be our value for x. So now we can go back to the Ka expression, and every place there's an x in it, replace it with 0.009772. Now in this case, you do not assume the x in the denominator is 0 because it doesn't save you from solving a quadratic. If you were to do that, you're just introducing error into your problem. So in this case, I directly plug the x values in and I calculate exactly what the Ka would come out to be. And in this case, to 3 significant figures, it comes out to be 1.95 times 10 to the minus 4th. Now, sometimes people will give you Ka values in a slightly different form. They will give you something called a pKa. Now, what would be the pKa of HA? What does that mean? What does a pH mean? pH means the negative log of the hydrogen ion concentration. What does pOH mean? The negative log of the hydroxide concentration. What does pKa mean? It means the negative log of the Ka. So if you want to write the pKa for HA, you just have to take the negative log of the Ka value. And I'm going to use a guard digit here so I don't round twice in my problem. But I'm taking the negative log of a 3 significant figure number, so I'm going to get a logarithmic pKa value that's 3 significant figures. So it'll have 3 places past the decimal point, and that comes out 3.710. So this would be the pKa of the acid. In general chemistry, we usually have tables that have Ka values. When you move on to organic chemistry, you'll find that when they're talking about acids, they usually have tables of pKa values. They find it just more convenient to write 3.710 than 1.95 times 10 to the minus 4th. Okay? Now, something to notice, the less the amount an acid ionizes, the weaker it is, and you have a smaller numerator. And if you have a smaller numerator, you're going to have a smaller Ka. So weak acids have small Kas. The smaller the Ka, the weaker the acid is. How's that related to its pKa? Well, if the Ka is really small, then the pKa is going to be a bigger number. So whether it's in general chemistry tables or organic chemistry tables. If you're looking at Kas, the smaller the Ka value, the weaker the acid. But if you're looking at pKa values, the bigger the pKa value is, the weaker the acid is. If you had a pKa value of 10, that would mean that the Ka was 1 times 10 to the minus 10th, and that's definitely smaller than 1.95 times 10 to the minus 4th. Let's try to calculate the Ka of an acid from some different clue, this time from percent ionization, which could be done by determining conductivities of solutions, so another experimental way to get at Kas of acids. Let's say a 5.00 molar solution of the weak acid HX is found to be 3.15% ionized. Calculate its Ka. So to get a Ka, we need to know the equilibrium molarities of all the species in the solution, and all we have is an initial molarity of the acid HX, so we're going to have to do an ice table for the reaction that corresponds to its Ka. That reaction is the acid HX reacting with water, producing a hydronium ion, and then the conjugate base anion X minus. The ice table will write for this the initial molarities, 0.500 for HX, and before it ionizes, it wouldn't have produced any hydroniums, and there wouldn't be any X minuses floating around in the solution. But as a weak acid, some of them do ionize. So if X amount of them do ionize, you'll create X molarity of hydronium ions and X molarity of X minus ions. So at equilibrium, you're going to wind up having 0.500 minus X molar of HX, X molar of hydroniums, and X molar of the X minus ions. These three equilibrium molarities are related to the equilibrium constant Ka. The Ka will equal the hydronium molarity multiplied by the X minus molarity divided by the HX molarity. And we know the equilibrium values from the ice table. Once again, we're in a situation where we have two variables and we need to solve for one of them first before we can get the other. So the clue in the problem that was given, it says the weak acid is 3.15% ionized. So how do we use that? 3.15% will equal the amount that ionizes, which is under the HX from the change line, X, divided by the original amount, 0.500, multiplied by 100. So the 3.15 equals the amount that ionizes divided by the original amount multiplied by 100. You can solve this for X. X turns out to be 0.0158, or with a guard digit, 0.01575. Now that you know what X is, we can plug those values into X into the Ka expression. And then once again, you do not ignore the X in the denominator. That would just be introducing error to your calculation of the Ka, and you're not saving yourself a whole lot of work. It's really easy to do a subtraction on a calculator. You'd only want to ignore that X in the denominator if it's going to prevent you from using the quadratic formula. So multiply all this out, and you'll get the Ka value for this to be 5.12 times 10 to the minus 4th. And then why don't you take a moment and see if you can determine what the pKa of acid HX is. So the pKa is going to be the negative log of whatever your Ka value is, which was a 3 significant figure number. So when you take the negative log of a 3 significant figure number, you'll get a logarithmic answer that's 3 significant figures, which means 3 places past the decimal point. So it should be 3.291. So we spent a good deal of time talking about what acids do when you dissolve them in water. They donate their hydrogen ion to create hydroniums as the waters accept them. Let's spend the rest of the time talking about bases. According to Bronsted-Lowry, bases are substances that accept hydrogen ions. So if you dissolve a base in water, it's going to take a hydrogen ion from water. Ammonia is a common base that I would like you to know. So when ammonia is dissolved in water, the ammonia molecule pulls a hydrogen off of the water molecule. It creates an ammonium ion, which is actually ammonia's conjugate acid. And the water molecule, having lost the hydrogen, becomes the hydroxide ion. And that hydroxide ion is the reason that ammonia creates solutions that are basic. The properties of basic solutions come from the presence of hydroxide ions. Why don't you see if you can write the equilibrium constant expression for this ionization of ammonia in water. All equilibrium constant expressions are products over reactants. So it should be the concentration of the ammonium ion multiplied by the concentration of the hydroxide ion divided by the concentration of ammonia. Whenever you write the reaction of a base ionizing in water, it's always going to pull a hydrogen off the water molecule. The water molecule is always going to become a hydroxide ion. Those reactions, we give the equilibrium constant a specific name. They're actually called base dissociation constants. So that's the equilibrium constant for the reaction of a base accepting a hydrogen ion from water. So anytime you're writing the reaction of a base with water, the equilibrium constant for that reaction is given the symbol K sub B because it's the base dissociation constant. And that's just a more specific name. It's actually still an equilibrium constant. It's actually still a Kc because it's the ratio of molarities. But because the reaction is so specific, they give it its own unique name. Now, in terms of bases, much as we talked about with acids before, bases can be strong if every single base molecule accepts a hydrogen ion from water. And if that's going to be the case, you will find the Kb's will be really, really large numbers. If a base is weak, and ammonia is an example of a weak base, it's a common base, but it's not strong, it's a weak base, that means less than every molecule or ion accepts a hydrogen. So that means you're not going to make very many products. The numerator is going to be a small number. The denominator is going to probably be a big number. And so the Kb's are going to be small. And so by looking at Kb values, you can once again just qualitatively judge whether the relative strengths of different bases. So if we're going to calculate the pHs of base solutions, we need to know if they're strong or weak because the calculation is different for the two. So if you want to calculate the pH of a strong base solution, you assume the base reacts 100%. So we assume complete ionization or dissociation. So what's a strong base? We know alkali metal hydroxides and calcium, strontium, and barium hydroxides are strong. So let me pick one of those. Let's calculate the pH of 0.0010 molar sodium hydroxide solution, which is a strong basis. So for bases, you have to write the reaction that produces hydroxide ions. When we had ammonia a moment ago, ammonia didn't have a hydroxide in its formula. So we write the reaction of ammonia plus water, and we have the hydrogen ion transferred from the water to the base, creating the hydroxide. Our strong bases are actually all ionic compounds, and the way we get hydroxides from them is the ionic compound just has its positive and negative ions separate from each other. So that it's actually a simpler reaction for strong bases. The sodium hydroxide, when it gets dissolved, would just produce a sodium ion and a hydroxide ion. And we can write an initial change and final molarity line for this. We're starting with a solution 0.0010 molar in sodium hydroxide, and before it breaks apart into ions, there wouldn't be any of the sodium ions or hydroxides. And then some amount of the sodium hydroxide will react away, and it'll form equal amounts of sodium and hydroxide. And we'd write X's here if we didn't know how much reacted. But it's a strong base. And a strong base, we assume complete dissociation. So we don't write X's there. We say it all reacts away. And because it's a 1-to-1-to-1 ratio, you're going to form 0.0010 molar of sodiums and 0.0010 molar of hydroxides. So once this has happened, in a solution of sodium hydroxide, there aren't any sodium hydroxide formula units, but there's 0.0010 molar of sodiums and 0.0010 molar of hydroxides. The hydroxide concentration allows you to calculate not the pH, but the pOH. pOH is the negative log of the hydroxide concentration, so you take the negative log of 0.0010, and that'll give you the pOH of the solution. That concentration is a two significant figure number, so our logarithmic number will have two places past the decimal point. The pOH comes out 3.00. When you're dealing with bases, a lot of people stop here and they go, that's my answer, I'm done. And if you think about it, you can't have a basic solution with a pH less than 7. And the reason this says 3 is that you haven't calculated the pH, you calculated the pOH. To get the pH, you have to go 14 minus 3 to do that, because the pH will equal the pKw minus the pOH. There's always one additional step then when you're dealing with basic solutions. You have to go the pKw minus the pOH, and that'll give you the pH of the solution, which in this case comes out 11.00. Once again, just as with strong acids, with strong bases, you really don't have to write an ICF table for this. If you assume complete dissociation, then if sodium hydroxide has one hydroxide in its formula, then you just go the molarity of the sodium hydroxide 0.0010 multiplied by 1, and that'll give you the hydroxide ion concentration in the solution. and then you can just go directly to taking the negative log of that. Now, what if you have a weak base? Well, weak bases do not dissociate or ionize completely. They actually reach an equilibrium. So you have to assume incomplete ionization or dissociation, and you reach a state of equilibrium, which means that the pH is going to be calculated with an equilibrium constant. Let's try an example. Let's calculate the pH of a 0.10 molar ammonia solution. So ammonia is a base. So you write the reaction of ammonia with water, and as a base, it pulls a hydrogen off of the water to create an ammonium ion and a hydroxide ion. Because it's a weak base, this reaches equilibrium, so I have a double-headed arrow written to indicate this will be an equilibrium problem. So I'm going to write an ICE table as opposed to an ICF table. Reaction does not go to completion, it goes to equilibrium. We have 0.10 molar of ammonia initially before it reacts with any of the waters, so we wouldn't have any ammoniums and any hydroxides. We don't know how much reacts because it's a weak acid. So it'd be X reacting away, you'd form X ammoniums and X hydroxides. Adding up the columns, we have 0.10 minus X, X, and X. These three equilibrium molarities are related to the equilibrium constant for this reaction, and the equilibrium constant for this reaction is called a Kb because the reaction is a base reacting with water. So the Kb is going to be products over reactants, ammonium molarity multiplied by hydroxide molarity divided by ammonia molarity. And if we have the value for Kb for ammonia, we can actually solve this. The Kb for ammonia can be looked up. It's actually also on handout 3. The top of handout 3 has lots of acid ionization constants, and the bottom of handout 3 has the base dissociation constants. So looking on that, you will find that the Kb for ammonia is 1.8 times 10 to the minus 5th. So therefore, 1.8 times 10 to the minus 5th would equal x squared divided by 0.10 minus x. Now, to solve this, we'd have to use the quadratic equation unless we make the assumption that the x in the denominator is going to be really small compared to 0.10. And because our constant, whether it's a Ka or Kb, is less than 10 to the minus second, that's probably going to be a good assumption. So I'm going to do this calculation instead. So if I multiply both sides by 0.10, then take the square root, I get my value for x, which is 1.3 times 10 to the minus third. Now we have to check to see if that was a good assumption. So I'm going to take what I got for x, divide it by the original amount of the base, which is 0.10, and then multiply by 100. So x divided by 0.10 multiplied by 100 equals 1.3%. And that's less than 5%. So that means we're going to assume that amount of error is okay. And we're going to assume this is the value for x. X stands for, in this problem, the hydroxide concentration. So if I take the negative log of x, I'm going to get the POH. So the negative log of 1.3 times 10 to the minus third will give me a 2 significant figure POH, which is a logarithmic number, which means 2 places past the decimal point. Once again, you don't stop here, because if you did, you'd go, wow, this base made an acidic pH. And that's because this isn't an acidic pH, this is a POH. To get the pH, you have to go pKw minus POH. So we go 14.000 minus 2.87, and that gives us a pH of 11.13.